Recall that we typically want to learn model f that maps from the input space x to output space y. In the supervised learning case, x is the data distribution and y the label distribution. Learning the model involves setting parameters theta such that the function performs this mapping well. We also use dataset D to learn model f. So, we can reframe our problem as trying to find an optimal set of parameters, theta star, for our model using the dataset. How do we actually go about finding this, and what does optimal mean? One way we might go about defining this is by taking the probability of the parameters given the data and saying that the parameters that maximize this probability are the optimal ones. The approach of finding parameters which maximize this probability is called maximum a posteriori estimation, and the resulting set of parameters are referred to as the maximum a posteriori estimate. We can also maximize the probability of the data given the parameters. Finding the parameters this way is called maximum likelihood estimation. Personally, I find maximum a posteriori more intuitive since it seems to align more closely with the goal of finding good parameters given the data that we have. But as you'll see in a bit, the two methods are related. If we look at Bayes' rule using the probabilities involving the parameters and the dataset, we see a relationship between the two probabilities we just discussed. These probabilities actually have names in the framework of Bayesian inference. We call the probability of parameters given data the posterior probability. The probability of data given parameters is called the likelihood. The probability of the parameters on their own is called the prior, and this probability expresses a belief about the parameters prior to observing the data. The probability of the data is called the evidence. This probability is typically difficult or impossible to calculate, so usually some trick is used to avoid its calculation. As promised, we will now show the relationship between maximum a posteriori and maximum likelihood estimation. Let's start with maximum a posteriori estimation and use Bayes' rule to express the probabilities as was just shown. Now, notice that the evidence, the probability of the dataset, is not dependent on the parameters theta over which we are trying to optimize. Therefore, it is constant with respect to optimization problem, and we can drop it to form an equivalent maximization problem. Notice that this is almost maximum likelihood estimation, except we have the prior probability and the parameters still there. If we assume equal or uniform probability of all the possible parameter settings, meaning we favor no parameters over others before seeing the data, p of theta is constant. So only when we make that assumption are we left with maximum likelihood estimation. So to summarize, maximum a posteriori estimation is equivalent to maximum likelihood estimation when the prior is uniform, and both of them are commonly used ways to learn a set of model parameters given a dataset.